All right, so these are the synthesis problems from the handout that I gave you. We'll just start with the first one. They get progressively a little bit harder as we go through. But the first thing I always do when I look at a synthesis problem is I determine whether or not the molecule I'm making has more carbons or fewer carbons than what I'm starting with. So if I look at the molecule on the right, it looks like we have 4 carbons, where this one has 2 and this one has 2. So that gives us a big clue that we need to somehow figure out a way of coupling these things together to get a chain length of 4 carbons, right? So does anybody have a proposal for how to do that? Yeah, so first thing we need to do is to deprotonate our alkyne. Right, so if we've got this alkyne, we can treat it with sodium amide. That will deprotonate one of those terminal protons, and we'll make an acetylide ion with a negative charge. And then in your next step, you can treat this with your ethyl bromide and do an SN2 reaction, right? This can attack the backside, kick off our leaving group, and now we've built up our carbon-carbon chain to be 4 carbons long. All right, we're one step away from getting to our final product, though. What do we need to do in order to get to this alkene? Yeah, we actually have 2 different routes. So we need to hydrogenate this alkene to get it. We need to hydrogenate the alkyne to get the alkene. And this isn't a cis or a trans alkene, so you can kind of choose whichever one you want. So you could do H2 in Lindlar's. Or, if you wanted to, you could do sodium and ammonia. That's the dissolving metal reduction. Because it's not a cis or a trans alkene, it doesn't really matter. You don't have to choose one over the other. Does that make sense? So this one's relatively straightforward. This is the only way we know of at this point in the year for adding carbons onto things. So if you ever see carbons getting longer over the course of a synthesis, you should immediately think, I need to alkylate an alkyne using this sort of strategy. All right, the next one, we're making the exact same product, but we're starting from an alkene. So that gives us a pretty good clue. In fact, let's work backwards using the same technique we did in the previous problem. We know at this point that our intermediate probably was something that looked like this. And just like in the previous one, you could use Lindlar's catalyst and hydrogen, or you could use the dissolving metal reduction. And we saw that we could make this alkyne by reacting the previous reagents that we saw. But then the question is, well, how in the heck do we make this from our starting material? So how do we make this from our starting alkene? Yeah, react it with HBr. So down here we can say, all right, let's make a note of how we would make this. If you have this alkene and you add in HBr, it doesn't really matter whether or not it's Markovnikov or anti-Markovnikov. There's not a more substituted side. And you can make ethyl bromide that way. So we've made that building block. All right, now the question is, well, how can we go from our starting alkene to this alkyne? Can we do it in one step? No. What might be a good strategy, though? Yeah, we need to add in some leaving groups. So if we add in Br2, we can do anti-addition of 2 bromine atoms. And now we've got 2 leaving groups that we can do 2 elimination reactions with to get our triple bond. What reagents do we need for that elimination reaction? Yeah, it's very similar to the pod. So if you ever need to make an alkyne from an alkene, you need to brominate it and then do a double elimination. So what reagent do we use for the double elimination? Sodium amide. So NaNH2, and we need excess of it, right? Because we're doing more than one elimination. And you could leave it like this if you want. However, typically you quench your reaction with water at the very end to get that. However, in this case, we can leave that out because we're purposely trying to leave this carbon without a proton in the very end. Does that make sense? So that's one possible strategy for making this same alkene. Any questions on the first two? Nope. All right, next one. Looks a little bit different. We're going from an alkyne to an aldehyde. So just like before, I like to count the number of carbons. So in the starting molecule, we've got 6 carbons. However, in our final product, we only have 3. That gives us a big clue that what sort of reaction is occurring. Ozonolysis, right? Ozonolysis is the one that we have available where we can cut things into 2 pieces. Okay, so if we think about ozonolysis, we can make an aldehyde using ozonolysis. So that would be O3 followed by DMS or zinc and water. All right, that means at some point, this carbon-oxygen double bond used to be a carbon-carbon double bond. So we can go ahead and we can say, all right, working backwards, maybe there was something here, and we don't exactly know what was coming off these ends. Doesn't really matter, though, but if we do ozonolysis, we'd be cutting that double bond in half, and we get an aldehyde out, right? Agree on that? We don't know what in the heck was on these positions, but that's okay. All right, so looking at our starting material, it looks like eventually what we need to do is we need to convert this alkyne into an alkene, right? So how could we do that potentially? Yeah, a poison catalyst. So for example, you could do H2 and Lindlar's. Would that give you the cis or the trans alkene? Cis. So then we would get our double bond there. It would look like this. All right, at this point, can we do the ozonolysis using this alkene? I think so. So if we count our double bonds, right? Or sorry, our carbons. We got 1, 2, 3 carbons. And then if we cut this double bond right there and compare it to our desired product, our desired product only has 3 carbons in it. So really what we can do is jump directly to our product by doing ozonolysis followed by a gentle reduction with DMS. So I'm just going to erase this for the time being. Would it have made a difference if we did dissolving metal reduction in this step? Yeah, it wouldn't have made a difference for our final product. It would have changed this intermediate to be a transalkene, but that ultimately didn't matter in the end, right? So oftentimes, there's not one right set of reagents to choose. You can use a variety of different pathways to get to the end. Does that make sense? All right, next one. Looks like we're going from a trans alkene to a cis alkene. All right, this one's a little bit tricky, but not too bad. How can we make a cis alkene? We know of one set of reagents where we can do that. H2 and Lindlar's. All right, that means that previous to this final product, this double bond used to be a triple bond, right? So we can go ahead and we can say, all right, this had to have been a triple bond. Looks like this. And now we've got to figure out how to get from our starting alkene, meaning the cis alkene, to that trans alkene. Or sorry, to the alkyne. I want to change colors. Either way. So what should we do to our starting material to get us to this alkyne? Yeah, Br2, kind of like we saw before. If you have an alkene, you can brominate it. we have anti-addition of 2 bromines. Now to get our double elimination reaction to occur, kind of like we saw before, you need excess sodium amide. That'll drive 2 E2 reactions. Does that make sense? All right. I don't know why it won't change the colors for that, but that's okay. All right. Jamie's favorite problem, number 5.
This one pissed me off.
So number 5 is a bit different than the other ones we've been looking at. If we look at our final product, it looks like we have 2 alcohols or a diol, right? So if we ask ourselves, what ways do we know of making a diol? We actually have, I believe, 3 different ways at this point. So let's try to come up with all 3 different options. So I'll call this one option A. We could use, does anybody want to throw one out? Yeah, MCPBA. Followed by acid. That would work. All right. Or we could do B. What's another way of doing this? I heard somebody say OSO4. Followed by sodium bisulfite. So that would work as well. And then last but not least, we had another one similar to OSO4. That was KMnO4, sodium hydroxide, and this would have to be run cold. All right, so now the difference lies in which one we want to select, right? Does it matter whether or not we select A, B, or C for this one? No, because we're not really making a syn or anti-diol, right? It's impossible to tell whether or not it's syn or anti, because right here, we don't have a stereocenter. So we can't definitively say whether or not it's syn or anti in this situation. So really, any of these 3 pathways would work. But just to review, which one would give you anti-diols? Would it be A, B, C, or D? A. So A would give you the anti-diol. What about B? That would be syn. And then C? Syn as well. But in this case, it doesn't really matter. All right, that means in this previous step, this highlighted bond must have been a double bond, right? So we can work backwards and we can say, all right, knowing that this used to be a double bond. So now the question is, how in the heck do we get from this starting material to a double bond in that position? Yeah, I would say tosylated. Right now, the alcohol is a super crummy leaving group. But that's okay. We can turn it into a better leaving group by using tosyl chloride and pyridine. And then this next step can be accomplished, but we have to be very particular about our reagents. What sort of reagent would we need to accomplish this elimination where we get the double bond in that specific position? Bulky base, right? What would happen if we use sodium hydride? Yeah, if we use sodium hydride, we would get our double bond there. We don't want our double bond there. We want our double bond on a less substituted position. So we do need to use a big bulky base. Something like terbutoxide would work well for this one. Make sense? So not too bad. Still 3 steps. Yeah. It's important to remember that in order to do elimination on an alcohol, you have one of 2 options. You can either protonate it and turn it into a good leaving group. That's normally an E1 reaction pathway. Or you can tosylate it and do elimination.
The problem we were having, though, is we were putting a proton on there, and then we get that positive charge, and then we saw that plus charge would go rearrange.
Yeah, so if you protonate this one, water would fall off, and then it would likely rearrange, and then it would give you the Zaitsev product, which, I mean, eventually you could get to this alkene. It would just require a lot more work, I would say. All right, next one. Looks like we're converting one isomer to another, so we're changing the position of the double bond. So this one's a bit trickier. Big thing we need to do is we need to install some sort of leaving group on our starting material. So now the question is, do we want the leaving group to go on to the red position or to the green position? What do you think? Yeah, I would say the red position, because that most closely aligns to where the double bond is in our final product, right? If we were to put it on the green position, we're not getting closer to that position. All right, so now how can we install a leaving group onto that red position? HBr and ROR are peroxides. So that does our anti-Markovnikov halogenation. Now we're actually one step away to our final product. How can we try to get that alkene, meaning our final product? Adding a base. What type of base? A big bulky base, right? We want the Hoffman elimination product. What happens if we were to use something like sodium hydride? Yeah, if we use sodium hydride, we just go right on back to our starting material. That's not what we want. We want to go to the other double bond. So you can kind of do this dance where you move functional groups from one carbon to another by choosing the appropriate reagents. Does that make sense? All right, next one. If we look at our final product, it looks like we have two alcohols. So again, this is a diol. And the way it's situated right now, it kind of looks like an anti-diol to me, right? Okay, so just like before, we already went over those reagents. To make an anti-diol, we need MCPBA, followed by treatment with acid and water. I'll just write H3O+. That means that there used to be a double bond on this position. Okay, so now we're running into kind of a weird situation, and I want your help with this. We either had an isomer where both ethyls were on the same side, or maybe it was this one. I want your help deciding which one was our intermediate. It does matter. Why do you think the left one? Because you like guessing. Yeah, if we look at our starting material, you see how both of these ethyls are on the same face? That means in the previous intermediate, they also would have had to have been on the same face, right? So in this case, these ethyls being on the same face here makes the most sense. All right, so knowing that, we can say with some confidence that this would be the most appropriate intermediate right here. This one's probably not the best intermediate. All right, so now we've got to figure out how to make that alkene from our starting alcohol. What do you think would be a good approach? Yeah, we could do kind of like we just did. We could treat this with tosyl chloride and pyridine. That would tosylate your alcohol. And then to get to this alkene, what reagent would we want to use? Do we want a bulky base or a non-bulky base this time? I would use a non-bulky base. Something like sodium hydride would work well. All right, my question for you though, this was a bit out there. Why can't we just treat this step with acid, catalytic acid, and heat? Does anybody know why? It would do E1, and E1 would favor your Zaitsev product, which is what we're getting. But if you protonate it, it turns it into OH2 plus, right? And that would be a good leaving group. So my question is, why can't we just skip this intermediate step and do catalytic acid and heat. This is more abstract. No, it would still be in that position. Give you a hint, it was something we just worked out before. Well, let's think about both of these have the Zaitsev double bond position. Which is the more stable alkene? Yeah, the right one is more stable. We know with E1 reactions, we always favor the more stable alkene as our major product, which in this case isn't what we want. So E1 for this particular reaction wouldn't give us the correct stereoisomer that we need for that final anti-addition step. So for example, we could say, it's probably not the best approach. It's probably better to use the tosyl chloride and pyridine. In addition, just to review, if you remember, our leaving group for E2 needs to be anti-coplanar to our beta proton. And during this process, this ethyl group and this ethyl group were both wedges, meaning they're both on the same face, and then they're both on the same face here. So now we've confirmed that we are in fact making our desired intermediate. So this one had a little bit more going on than some of the other ones. Like I said, I progressively make these harder as we go through the activity set. Any questions? All right. I think this one was our challenge problem. We've got to figure out how in the heck to make this. So this one I thought was the hardest on there. First thing I noticed, though, is my final product has many more carbons than my starting material. So what does that indicate? We're going to need to make an alkyne and do some sort of alkylation, right? So let's just do that really quick. We know how to make an alkyne. We've already done this before. First, we can brominate. And then next, we can make our alkyne. And quench it with water. We saw that in our previous problem set. All right, it looks like the longest carbon chain that we've got is about 4 carbons long, right? So 4 attached carbons in a row. So it looks to me like this alkyne that we made, we need to add 2 more carbons to. But we've actually done this in our other problems, where we deprotonated the alkyne, and then we treated it with ethyl bromide. We did that in our first problem, right? And our second problem. So this is kind of bringing them all back together. All right, now's the tricky part. How in the heck do we get to our final product? Well, if we look at this, we've got 4 carbons right here. To me, this must have come from the 4 carbon part of that molecule. So we've got to figure out how to attach something to one of these carbons. Whoops, sorry, wrong carbon. We've got to do an addition reaction and get something installed there. Does anybody have ideas? So if we did ozonolysis, we'd make a carboxylic acid, and we'd lose one of those carbons. We don't want to lose any of those 4 carbons. So we could add an alcohol onto that carbon, but it would be an enol, right? And we saw that enols quickly tautomerize to, in this case, a ketone. We don't want a ketone for our final product. So I'll kind of give you a hint. What I would do is change it to that alkene that we previously made. So now we've got 4 carbons. You could do this with H2 and Lindlar's. All right, we need to add an oxygen into the more substituted side of that alkene. How can we do that? So we want to add this oxygen onto the second carbon of our 4 carbon chain. How can we do that? So if we did hydroboration, we would actually favor the least substituted side. So we need to do a Markovnikov addition of oxygen. So we could do oxymercuration, or we could just do acid and water. As a chemist, I would like to avoid using mercury because I like not dying of cancer. So I'll just do acid and water. All right, so now we've got our alcohol. We're almost there. Now we've got to figure out how to get these last two carbons onto that oxygen. This is really going back to last term. We could do substitution. But I would say that this right now isn't the world's greatest nucleophile, right? It would be a really weak nucleophile. We need a strong nucleophile for substitution. How can we turn that alcohol into a strong nucleophile and give it a negative charge? Yeah, drop the H. So we need to deprotonate it. Okay? So to deprotonate this alcohol, you could do a bunch of different things. We could just use sodium hydride, for example. If we do that, now this oxygen has a negative charge. We need to get those last two carbons that I've circled in green here on. So we need to have something for that oxygen to attack. So for example, in this last step, you could say, well, maybe what we did was react this with ethyl bromide. This oxygen could attack that backside, kick off the bromine, and get us to our final product. So I will say this was definitely the most challenging problem on the problem set. Normally I don't make them this hard this soon. On the first exam, I want students to show me that they are beginning to understand synthesis. Speaking of that, I've posted the practice exam already, so you can look at the synthesis problems on there and kind of use some of these strategies. The other thing too is with synthesis problems on exams, I'll mention this when we do the practice exam. If there's a common intermediate, you can just say C above and I'll understand. So for example, what I mean by that is this intermediate right here, we made in our first two problems. So if you run into that situation on an exam, you can just say C above for the intermediate formation. I'm fine with that. That can save you a lot of time. That way you're not just repeating yourself over and over again. Make sense? All right, I threw on a few more practice ones that are more related to this last chapter, because I know everybody likes extra work. So if you want, I'll give you a few minutes to think about these. I will say that the starting material doesn't even have a functional group on it. It's just an alkane. What do you think your likely first step will be? What was that? You're like, I don't want to be loud and wrong. I'd rather be quiet. So we can't make an alkane go to an alkene directly. That's impossible. But we can install a leaving group on an alkane. How do we do that? Not HBr. Br2 and not water. We need to cleave the bromine, make radicals. So Br2 and UV light. So we may need to do radical chemistry to get a leaving group on our starting materials here. So I'm going to pause it and then let you work on these for a minute. All right, so let's look at these additional ones. Going backwards, if we look at this one, we saw a reaction where we could add both a bromine and an alcohol at the same time. However, we had to have had an alkene where that highlighted position is, right? So we know going backwards that our intermediate must have looked like this. And how can we install both the bromine and the alcohol in an anti-orientation for an alkene like that? Br2 and water, that's our halohydrin reaction. It's important to remember that with the halohydrin reaction, your alcohol always prefers to be on the more substituted carbon, right? All right, we can't go directly from our alkane to our alkene. However, what we can do is we can install a leaving group on our more substituted carbon. Let me spread this out. And then we can make our alkene that way. So now the question is, how do we install that leaving group? Yeah, Br2, not HBr, and then UV light. So that would install your halogen on your more substituted carbon. And then to make that alkene, looks like we need to do an elimination reaction. How do we want to do that? Sodium hydroxide? Yeah, you can use, honestly, any alkoxide, whether that's hydroxide. Why aren't we worried about, let's say, SN2 reactions if we use sodium hydroxide? So hydroxide is both a good nucleophile and a good base. But why won't it do substitution here? It's a tertiary carbon, right? If this hydroxide were to try to attack here, that's super duper hindered, just not going to happen. So it's going to favor E2, and it's going to favor your Zaitsev product. We don't, however, want to use a big bulky base. Otherwise, that would give us our Hofmann elimination product. So not too bad for that one. Let's do the next one. Next one, the first thing I notice is we started out with 3 carbons, and we're ending up with 2 carbons. That gives us a big clue. What do you think happened at one point?
4 carbons to 2 carbons.
Yeah, 4 carbons to 2, sorry. So we must have done ozonolysis at some point. So if we think about it, what sort of functional group must we have had in this intermediate step before ozonolysis? An alkyne. So if we do ozonolysis of an alkyne, that would give us a carboxylic acid. So we've got carbon 1 and 2. That means that we must have had 2 carbons and then an alkyne and then something coming off the end, right? So there must have been 1, 2. The third carbon is going to end up getting lopped off on the other side. We don't really know exactly what was in this position. All right, so now the question is, well, how can we turn this starting material into an alkyne? Well, we don't have any functional groups on it, but just like before, we can halogenate it using elemental bromine and UV light. It's going to brominate one of the more substituted carbons, in this case, one of the secondary carbons. Doesn't matter. And then what we can do is do an elimination reaction. But if we look at this one, we want eventually some sort of pi bonds to be between carbons 2 and 3, right? So we want to make our more substituted alkene, meaning our Zaitsev product, not our Hofmann product. So do we want a big base or a small base? Small base. So for example, our major product for this example would be an alkene. However, like we saw before, we want to make an alkyne. So how can we go from an alkene to an alkyne? Yeah, we can brominate it. Okay, if we do that, now we've got anti-addition of our bromine. We're almost there. Now we need to figure out how to go from this dihalide to our alkyne. So how can we accomplish that? Yeah, sodium amide. So I'm just going to erase this and then we'll plug it back in. So if we do that, now we have our 4 carbons, and if we do ozonolysis, just like before, we'd end up with 2 carbons that have a carboxylic acid on it. Does that make sense? So a little bit trickier, more steps involving all 3 chapters that we've covered this term. All right.
On the ozonolysis, first, why do we need water?
So instead of using DMS for the second step with alkynes, you just need water. These pop apart really easily. Yeah, it's a subtle difference. If you use DMS, it's not the end of the world.
Okay.
Yeah.
On the test, we don't know what the ending group
I was just doing that just to logically walk backwards. So that question mark was just to say we don't know. However, it makes sense that it would have been a methyl group based on the starting material being 4 carbons long and not longer, right? So we've got 3 and then 4. Going backwards, though, what do you think happened to this end? Yeah, we made 2 equivalents, right? So we could have said for every 1 mole we put in, we got 2 moles of our product out. It just happens that both of the carboxylic acids in this case are identical. All right. Now going down to the next one. Looks like we've got, oops, sorry, this should be an oxygen here. Sorry about that. That probably made that problem much harder than it needed to be. All right, so looking at this one, we've got to figure out how to make this ketone. We've seen a few ways of making ketones. One was ozonolysis. The problem with ozonolysis I'm seeing here is we started out with 4 carbons and we're ending with 4 carbons. So to me, that probably means that ozonolysis isn't super likely. So what was another way we knew of for making a ketone? Yeah, so we could have had what sort of functional group if we were using H2SO4 and HgSO4? What functional group must have been the intermediate? An alkyne. And then, if we think about it, we just made this in that previous problem right here. So we could say C above. So like I said, on exams, you're more than welcome to do something like that. That way you don't have to re-show everything that you previously showed me. What happens in this problem if we were to use 9-BBN? Would we? So let's think about it, right? We've got the red side here, and we've got the green side here. Is there a Markovnikov or anti-Markovnikov position? No. So you could have done either method. You could have used the 9-BBN method or this method. Doesn't really matter. Either one would work. All right. And then the last one, if we look at it, we started out with 4 carbons. We're ending with 3. That gives us a big clue. Probably had some sort of ozonolysis, followed by DMS. And do you think it was an alkyne or an alkene? Yeah, it was an alkene. What happens with alkynes? Do we ever get aldehydes? Yeah, we get carboxylic acids. So this must have been some sort of alkene. So for example, if we did this alkene and we chop this off, that would give us our aldehyde, right? Okay, so now the question is, how do we get from our starting material to that alkene? Well, we know if we have an alkane that's unfunctionalized, we got to functionalize it before we can do anything. Only way we know of at this point is to brominate using radical bromination. And now we've got to show how to get from this alkyl halide in the bottom left-hand corner to this alkene. How can we do that? Terbutoxide. We do have to use a big bulky base because we want to favor the Hoffman product here, right? So TBU-OK would work here, potassium terbutoxide. So not too bad, 3 steps for this one. Yep.
So if you ever have more carbons going down to less carbons in that double bond on oxygen, then it's ozonolysis. But if it's less carbons going more, then we're doing the oxidation.
Yeah, so your question was about the number of carbons. So if we're losing carbons over the course of a synthesis, chances are ozonolysis is occurring. If we're gaining carbons, that likely means, using the chemistry we know now at least, that we had an alkyne at some point that we deprotonated and then had to do an alkylation reaction with an alkyl halide. So kind of like these first reactions that we looked at, we gained carbons, we had an alkyne, we made an acetylide ion, and then we reacted it with an alkyl halide. So that's our only method at this point in the year for adding carbons in. So that gives you a big clue when you're working through synthesis problems. Does that make sense?
When we did the rotation, we said there was another way to do that product.
Oh, so, sorry, going backwards. You're asking about this step, I think?
Yeah.
So you could use this one, or you could do 9 BBN, NaOH, and H2O2. So hydroboration oxidation in this case would give you the exact same product.
Water or peroxide?
Oh, sorry, peroxide. Because this carbon right here is equally as substituted as that one. One side's not going to be favored, so you can choose either one. Yep. All right, so I think we'll call it good for today, but if you have any questions over the weekend, you're more than welcome to email me.